You would think Elon Musk's state light traveling to Mars at 60,000 miles per hour would create a wind resistance, but in empty vacuum, its oath trajectory does not create inertia. That is a great observation about how motion works differently in space compared to everyday life on Earth. The reason a spacecraft or satellite can travel at tens of thousands of miles per hour without experiencing wind resistance or slowing down comes down to a few fundamental physics concepts. The absence of atmosphere, wind resistance, or drag is caused by air molecules colliding with a moving object. In the vacuum of deep space, there is virtually no air, meaning there are no gas molecules to push against. With zero atmospheric friction, the spacecraft doesn't need to burn fuel continuously to maintain its speed. Inertia is actually at play. Newton's first law of motion states that an object in motion tends to stay in motion at a constant velocity unless acted upon by an outside force. Inertia is precisely why the spacecraft keeps moving. Once the rocket engine shuts off, the craft continues coasting along its trajectory indefinitely because nothing is slowing it down. Gravity and trajectories. While there is no air resistance, space isn't completely empty of forces. Gravity from the Sun, Earth, Mars, and other celestial bodies constantly exerts gravitational pulls on the spacecraft, which bends its orbital path, its trajectory over time. But this shapes its route rather than creating a headwind.
I keep hearing this idea. Inertia is like a built-in engine. Space vacuum carries your ship, so propulsion is just speeding up the ride. Sounds cool. It's also not how physics works. Here's the myth versus physics in 120 seconds. Myth: inertia is a propulsion force, and the vacuum has a carrier that frees your velocity. Physics: inertia isn't a push, it's a personality trait of matter. Resistance to any change in motion. The more mass you've got, the more stubborn you are. Think of a spaceship. If it's massive, I need more thrust to speed up, slow down, turn. That's inertia talking. But once I cut the engines, Newton's first law takes over. The ship keeps cruising at the exact same speed and direction. No secret hand of space helping. What about the vacuum? A vacuum is just nothing. No air, no friction, no hidden conveyor belt. Since there's nothing to rub against, there's also nothing to slow you down. That's why I only burn fuel when I want to change velocity. Accelerate, brake, pivot. No change, no thrust. So where does motion come from? Momentum. My engines push propellant out the back, the ship pushes forward. That initial push sets my speed. Turn the engines off, and I coast, indefinitely, because nothing's fighting me. Quick gut check. Inertia. Resistance to change, tied to mass. Propulsion. Arg, what changes velocity? Vacuum. Arg's absence of stuff, not a force. If I want to speed up, I push harder. If I want to stop, I push the other way. If I want to just glide through the dark, I do nothing, and inertia keeps me honest. Myth: vacuum carries you. Physics: you carry your motion until you choose to change it. That's the whole trick of spaceflight, and it's beautifully simple.
Einstein's geodesic is not measured. The tension between celestials, planets, and galaxies are astronomically far. The nearest distance to our Sun is 93,000 miles. Distance to our nearest moon, 240,000 miles. Relativity theory geodesic theory is based on microscopically close distances. That, as you can see, is real far instead. The quantum physics theory where geodesics apply. Astronomy versus the microscopic. While the distances between celestial bodies are indeed vast, such as 93 million miles to the Sun and 240,000 miles to the Moon, Einstein's theory of general relativity and its concept of geodesics are actually designed for and tested on these massive astronomical scales rather than microscopic ones. Orbits as geodesics. In general relativity, planets and moons do not follow a traditional pulling force. Instead, they follow natural, unforced paths, geodesics, through a space-time grid warped by massive bodies like the Sun and Earth. The Earth traveling its 93 million-mile orbital path is a direct, large-scale demonstration of a geodesic in action. Precise measurement. We continuously measure these cosmic paths with extreme accuracy. For instance, scientists use laser-ranging bouncing-off retroreflectors left on the Moon to measure the Earth-Moon distance down to the millimeter, tracking its precise orbital behavior. Furthermore, phenomena like gravitational lensing show how light from galaxies millions of light-years away bends along space-time geodesics, the microscopic limit. Ironically, general relativity actually struggles at microscopic scales. At the subatomic level, quantum mechanics takes over, and gravity is so infinitesimally weak compared to other forces that Einstein's geometry is rarely applicable there. It is precisely the large-scale universe, stars, planets, and galaxies, where relativistic physics shines.